Sorry, the last recording, I accidentally ended the last recording. Okay, so, what is going on is, yes, you have a stationary phase, which is your adsorbent. So I'll just add that. And the mobile phase. Okay, so again, going back to what you guys did in your lab. So if you expect mobile phase, if you have 100% of your mobile phase, if something really likes the mobile phase and adsorbs will interact more with your mobile phase, then you will get a higher RF value. So RF, if it's higher, that means it likes the mobile phase, and hence, because it interacts more strongly with the mobile phase, and your mobile phase is more nonpolar, you can tell that your compound is more relatively nonpolar compared to other components that you have where your mobile phase is low. I mean, your RF retention factor is low, which means it interacts more strongly and less strongly with the mobile phase, and it adsorbs more to the stationary phase, which is polar. So you can expect it's just more polar. And it's important to know what adsorption, elution, and different types of terms like that mean. So elution just means you're like the ability to like move in a sense, elute. So this means if you have higher elution, you're more you're moving with like the mobile phase. Adsorption is like a little different. So adsorption means you like to stick to your stationary phase. It's not absorbing, it's adsorbing, so it's a little different. So nothing is like getting absorbed like a paper towel soaking up liquid. It just means nothing is like getting soaked up, but it means you're interacting strongly with your stationary phase, and so you just like you're on a surface. Nothing is like penetrating anything, but how well you stick to the surface. So you can kind of think of it like friction, like maybe like oh, I don't want to like move, trying to push something, and then you feel the resistance, kind of like that. Okay, so once again, these are different definitions to note. The RF, I'm going to talk about the retention factor a little bit. So RF equals the retention factor, which is the distance the sample traveled, or solute travel, elution distance. And it might be in centimeters. The distance over the distance the solvent or your mobile phase traveled. I know my handwriting is not the best, and so because you do distance divided by distance, retention factor is dimensionless. There's no units, like unitless. So just note that. Yeah, so solvent, solute over solvent. Okay, and then here you can see that, for instance, the solvent distance, it will be this, the line to line. You just draw it for easy measurement. So this line is your solvent distance, and then your solute distance is however much this green thing I drew up traveled. So like maybe this is your solute traveling distance. And you might have multiple spots, so you have different RF values for each. And then by where your spot is located and your RFs, your relative RFs, you can compare them. So I'm gonna go back to your extraction experiment. So you might notice, okay, I have 3 spots, and this is what I would expect ideally. 1,4-dimethoxybenzene is is least polar because it's organic, so you would expect it to have a high RF value. 2-naphthol is like less polar, but less polar than 3-nitrobenzoic acid, but more polar than 1,4-dimethoxybenzene, and your 3-nitrobenzoic acid is the most polar, so you would expect this. But this might not always be the case, and you might have residue. So for instance, like I could have residue here or like here, and if I had these 3 spots, I know like, oh, of course I didn't separate out just 2-naphthol. I have 2 other components, and how concentrated the spot is, how dark it is, kind of tells you how much you have, but like that's not easy to note. So it's kind of qualitative in that sense. Okay, and then again, polarity is very important. So again, you can assess purity here, and you should know the relative polarities between your solutes and your solvent. Like, so if you have different components in your solvent, your mobile phase, you should note those. I will talk a little bit more about retention factor later. Okay, so also you might have used a UV lamp to determine where your spot is, but you can also look at it by your eye. We use a UV lamp for the extraction samples because you can't really see anything. But then for your TLC with spinach pigments, you can see the pigment colors. So you will assess them by just an eye, like just looking through your eyes. Okay, so if you see page 33, they do give you a distribution of different affinities in a sense. So elution power. So affinity is like what you like to interact with. So you have hexane, dichloromethane, okay, so you see you have these components, and it said low affinity or eluting power up here, and a higher affinity and or eluting power up here. As you can see, hexane is the least polar of all these compounds, and methanol is the most polar. So most polar, and you have least polar. And usually you'll have a mixture of these. So you guys used in your lab hexane and acetone. So you guys used these 2 components. You use a mixture to create that the concentration gradient, or polar, not concentration gradient, a polarity gradient. And then also you will see on page 34, there's a really helpful guide on different functional groups and polarity. So you should know how the trends of different functional groups in terms of relative polarity. Let me make sure I'm recording. Okay. So you can see the first thing you have is carboxylic acid. They're very poor carboxylic acids. Then you have alcohols. Then you have amines. Then you have carbonyls, ketones, esters. You have ethers. And you have alkenes, and you have just alkanes. do X. And so here, what you notice is this is most polar. So it will adsorb best to your stationary phase, or you will have the lowest RF. And then this is the least polar, adsorb least, elute most. RF will be higher. So hopefully that helps. Adsorb best to silica, elute most, adhere most, have a greater affinity to the mobile phase. I know all the terms can be a little confusing. Okay, and then, so you have the 4 pigments, chlorophyll A, chlorophyll B, xanthophyll, beta carotene, and you will probably have noticed that the xanthophylls was most polar. Then you have your chlorophylls, which don't, so chlorophylls are harder to separate because they are very similar, except chlorophyll B has a heat aldehyde, and your chlorophyll A has a methyl group, and so your chlorophyll B will be more polar than A, and then beta carotene, which is the least polar. So knowing those will be helpful. So again, chloro, so you have xanthophylls, chloro B, chloro A, and then you have carotene. So the RF would be, you would expect RF to be low, highest here, and RF to be lowest here. And xanthophylls can be hard to see sometimes. I believe these are green and this is yellow or orange. I'm not sure 100% about colors. And then you did a class TLC, and so when you did the class TLC, you probably noticed this is another important trend to note. Okay, so you were testing different mobile phase compositions of acetone to hexanes on the separation that you get. And so, let's say this is my TLC. Okay, so what's going on is if you have 100%, let's say you had 100% acetone, 0% hexanes. So I'll just use different colors to help make the point. So if you had 100% and 0%, for those who did that, you would notice that the acetone using this phase with the components meant you had no separation. All your components in your sample, so spinach has all 4 samples in it of pigments, or spinach sample has all 4 pigments in it, and you want to separate out pigments, you would realize all 4, there was no elution, it just went straight up. And you probably got an RF of like 1. But let's say, so I will just say RF like 1, no separation, everything just eluted. And okay, so let's say we repeated this and you had okay, so we repeated this, and then this time you had 0% acetone and 100% hexanes. So what happened here is nothing eluted because it's 100% hexane. So if you think about it, it's all non-polar, and some of your components are polar, and you elute based on like your interactions, polar kind of interactions. So because you have no polarity, or you have no like driving, I guess driving force, or like you have no push to like kind of elution power. You have like no elution power. You can't elute anything. So once again, going back to that, back to this where we kind of skipped through it. So it says low affinity. So hexane has a low affinity for the stationary phase. That's what it means. And it has low elution power. And so that's why we see a RF of 0. Nothing is going to elute. And here we have a high affinity. So high elution power. And that's why your acetone, when you use the acetone, 100% acetone mobile phase, it just went, all your components went straight up. But there was no good separation because it was way too polar and everything just interacted with a polar phase. And the polar mobile phase, and you didn't have any interaction with the polar stationary phase. And so what we expect is the dot just stays here. So RF equals 0, and you still have no separation. And these two are not ideal. So we don't want that. And then so then you tested all your other compositions, and then you probably start noticing I'm starting to get better separation, like when I'm close to moving away from this 100%, 0%, and I'm also getting better separation moving up. And then we kept going, and you probably then in the middle somewhere you had like all 4 spots using a composition in the middle of those two. You had like all 4 spots, and probably noticed that your best TLC mixture was made of like 45-55 acetone, hexanes, 35-65, something like that, maybe 50-50. So we could just say around like 50, 45, 55, like one of those. Yeah, so it might have been like one of these. I'm not sure what you had, but that was your best TLC. And then you also determined the worst TLC, which was one of these. Okay, so the reason why you might notice it's not, why is it not 55, 45, why is it not like 60-40, why is it like usually lower for acetones and higher for hexanes? The reason for that would be because you want it a little bit more non-polar. Remember your stationary phase is polar, so you want to be a little bit more on the non-polar side. You still need polarity, so that's why you have acetone, which is polar protic solvent. So yeah, that hopefully helps. And you probably, and again, you will have noticed there's like 4 RF values you calculate. And then probably notice that this is xanthophylls, this is chlorophyll B, chlorophyll A, and this is your beta carotene based on polarity. So again, here's least polar at the top, more polar down here. And RF down, RF up, higher RF. Okay. So also, if you're given distances, you should be able to separate, you should be able to calculate the RF values. So if this was like, let's say 3.7 and this whole distance was like 8.1, then you could do something like 3.7 divided by 8.1 and you get like 0.456. So something like that you can do. And then by your RF values, so if you had multiple components, let's say we did another component here and then we got separation and this is like maybe unknown, then I can just match the RF values with a known and figure out what my component is. So after I do this, I know what this is. And if I have residue of something else, so you can use it in that sense to identify unknown components by RF value, assuming they're on the same TLC and you're using the same mobile phase composition. If you use a different one, the RF values can get can change. So this is all relative on like one TLC plate. Okay. So okay, I'm going to talk about column chromatography now. So okay, so column chromatography is slightly a little bit different from your TLC. So here's a column that I have. We abbreviate it LC for liquid chromatography. And here it's a little bit different because you're eluting down. So elution goes down, whereas your elution was up in TLC. And then something that's adsorbing more will slow down your elution, so you can kind of like think of it like it's not gonna elute as fast. I don't want to say up because it's not, nothing's going up, but it tends to stay like up here. It will elute less. And once again, you have your mobile phase, which is still acetone, hexanes. And let's say we had the best mixture composition be like 45, 55 acetone hexanes. And then, like, let's say we determine that from the previous week. Then you also tested something like 1090 or maybe like, let's just say 3070, so something that has more hexanes, so more nonpolar. The reason for this, and you probably should have noticed that this gives you a better separation than this, and the reason for this is you have, in TLC, you're eluting upwards, you're going against the gravity, but here, you have gravity. Like maybe TLC is defying gravity and liquid chromatography is not, but your gravity is on your side now, so of elution, so it's gonna speed up everything. And if you think about gravity impacting your separation, is pushing everything down, meaning like while some of them are trying to slow down, some of the components want to slow down and adsorb more, and then some elute faster. Like gravity just has that same impact. It treats everything equally, kind of like maybe like a curve. Maybe you're excited for curve for the class, but like curve kind of impacts everybody the same. Maybe not saying anything about any classes, but basically the gravity is applied to everything, so everything's gonna get pushed down faster, and it speeds up everything. And here you don't want it to speed up. If you have the more time you have, if you imagine like pushing everything down in 1 second, you're not gonna get a separation, but you want more time to be able to get a better separation. Kind of like if you give more time to do a project, some people are going to do it slowly and some people are going to do it fast, and you can really see who procrastinates and who doesn't. But like if everyone has like only 1 day to do it, you can't really tell who's doing it ahead of time and who's not. So kind of like that analogy, like you want better separation, so you want to give it more time, but gravity like goes against. So gravity kind of decreases the time to separate. Okay, so you might remember or recall you have your different components. So you put the cotton, put like a cotton down here because you don't want like samples, the sand going through and all that. And then you have a whole layer. You had some silica, then you had some sand. You also have some sand down here, I think. Then, I'm sorry, this is your silica, no, sample. So, and okay, you had a sample up here, and the reason why you had to have another layer up here of sand is because you want to cushion your sample, and you don't want like when you're squirting your liquid down, you don't want like push through your sample like unevenly. You want everything to flow down evenly, so you want the whole layer moving down. You don't want like different components moving down like that. That causes different flow paths, and this is gonna cause your sample not to be not to separate well. So you don't want that at all. And then once you have this, you might have separated, you also pushed it down through like the sides of the wall, so it gently pushes down. You don't want like turbulent, I guess, like, or just fast flow. You want it to be just slow and easy, nothing accelerating. And then so over time, you can also notice that another method in increasing time is, if you think about speed and time, let's assume the speed is the same, impacted by gravity and the mobile phase composition. But if you increase the column length, so if it was like longer, there's more time to separate. So that also gives you better separation. So let's say if you increase the column length. Another thing that will give you better separation is, once again, making your component, your composition a little more non-polar, just because it slows down the impact. It counteracts the impact of gravity pushing down. So if it's more non-polar, you're going to have more adsorption, so things will stay up a little more, so it'll kind of like elute more slowly. You're giving it better, like lower elution power to counteract the higher elution power of the gravity. And then once you have different components, you switched out like a flask or receiving vessel, and you might have gotten like component that's supposed to be a flask. So component A, component B, C, D. So you have like all 4 components here. So we would expect this first one to be the first one to elute. It's kind of a little opposite. So retention time and your retention factor are a little bit different. So higher RF means that you elute faster, meaning your retention time is lower. So and the same thing with the opposite. So if you have a lower RF, you have more adsorption or less elution, and then your retention time would be more. So using that principle, we assume the first compound you extract is more nonpolar because remember your mobile phase is nonpolar, your stationary phase, the silica is still polar. So the most nonpolar component we had was carotene. Then we assume this is chloro A. And then we assume this is chloro B. And lastly, we assume this is xanthophylls. And if you had trouble getting xanthophylls out because they absorbed too much of silica, might have put some pressure like a rubber bulb and pushed it through at the end. Okay. Also, remember you use like a TLC spotter or acetone to dissolve components and then spotted them. And then once you had these 4 samples, we're doing the exact same thing as experiment 3. It's assessing how good of a job we did for separation in experiment 3 with extraction results. The TLC part of the liquid chromatography, which was the second component, wasn't the principle of separation. The principle of separation, I think this is a big point to take note of. So this is column chromatography. The principle of extraction, the principle of separation was extraction for these 3 compounds. The same thing here. The principle for extraction, the separation was column chromatography. So you were separating by doing column chromatography. You weren't separating by doing TLC. The TLC, well, in experiment 4, you did do separation by TLC, but here, there's nothing to separate if these were all pure components, right? If these were all pure, what are you even separating? Like, there's no point in doing that. So essentially what you were doing in the TLC is you had 1, 2, 3, 4 samples separated, and you had your pure sample, but that's just to kind of do the identification kind of thing. So you might expect this. So if the RF was lowest, we assumed that's xanthophylls. So this was xanthophylls, this was chloro B, this was chloro A, and then the last one was your carotene because it had the highest RF, and this is your spinach. No, my handwriting's not the best. And then all we were trying to do, it might have not been perfect like this, and you might have had residue. So you just look at the samples, kind of want to match them up. I'll use the same color scheme. So I had carotene as like light blue. So these samples, chlorophyll A, this is chlorophyll B, and then let's say the red one was xanthophylls. So maybe the color might help. So you had fraction 1 that eluted first, fraction 2 in your second one, fraction 3, fraction 4, and then you had your pure spinach sample for like just cross-analyzing them. And from this, if you had multiple spots here, let's say I had another spot here for my 4th fraction, then I know the xanthophylls, I moved the column too early, and then I had some chlorophyll B. I didn't leave the previous vessel to collect all the chlorophyll B, and some of it kind of dripped into the xanthophylls, and so I have that impurity here. So you should be able to analyze things like that. So it is used as the check for purity. The TLC in experiments 3 and 5 are used for check impurity. For experiment 4, it was used as a principle of separation, but just make sure to have that clear. I think that mainly what I had. Oh, another thing you could do with column chromatography is you can start out with a less poor solvent. So you could use a less poor solvent. So you could use like 4555, and then if you wanted to change it to you can change it to a more polar eluting solvent. So maybe you started with 3070 and then you kind of gradually increase the amount of acetone. So you made it 4555. You can do a gradient elution. Not a huge important detail, but you could start more nonpolar. And as your nonpolar stuff comes out, if you wanted to speed it up, if you made it more polar, you know, it speeds up and all you have is left is polar stuff, so you could do a gradient elution here if you wanted to. Another thing, okay, so I'm gonna just add some factors. I will type it because my handwriting is not great. So longer column. What are things that help you separate? You have a longer column because you have more time to and you have more adsorbent to interact with, and so you'll have more time for separation. Larger diameter columns. Because your volume of your sample is concentrated to that band. So when you have that, that's a smaller fraction of like your total volume. So you will have just better separation. You smaller sample. These are some things that should be noted. Smaller sample volume. Once again, because you have a smaller fraction of the column volume, so you want the sample to be as small of a fraction of the whole volume as possible, just to give yourself more separation. A more concentrated sample will also give you a better separation. So you want the like when you dissolve your spinach into acetone and like crush it up, you want the sample to be a smaller layer, because if you had more of the sample, if it was less concentrated, then it's like more difficult to separate out. So more concentrated sample. Yeah, so you want less diffusion. So that's also another reason for 2 through 4. And another thing is you want to counteract gravity, so more non-polar is better. Yep, and then remember the relative orders were different. Carotene. So carotene eluted first, but it went down first because remember elution went down here and elution was up here. So like carotene was the highest point, carotene was the lowest point in the column, carotene was the highest point in the TLC. It's still the highest point in the TLC, but just note carotene was first. Here too, it went up first. So just to like match those up, they have different directions. Okay. And then I'm gonna talk slightly about the post-lab questions. Okay, so you can see here's the post-lab questions. So it says student obtained the TLC plate below from the 3 solids of the extraction experiment. However, he forgot to label which solid which was which spot. So once again, as I said, you can kind of use the relative to, so this type of problem is valid. You can use relative polarities. So use the I believe it's the like chart on page 34. You assess the functional groups. and figure out what the relative polarity is, and then you can find the order here. And you can see there's like 3 different RF factors that I could have, which match the 3 components. Another thing is if you had run like just the original extraction mixture and then you had all 3 points, so something like this, you can just kind of cross-analyze them. So you know all of these are the same and all of these are the same. And this is the most polar, so which has the lowest RF, so I would think this is 3-nitrobenzoic, this is 2-naphthol, and this is 1,4-dimethoxybenzene. Okay, and then calculate RF values. Once again, you should know how to do that. Are the 3 solids pure? Again, I'm looking, so when you're assessing purity, you're not, so when you, maybe this might help. So when you ID mixtures, you look across. So these are all the same components horizontally. When you are analyzing when you're analyzing for purity, however, what we're looking for is not this. This is not what we're looking for. We're looking within each band, so each fraction. So the first one, not pure. The second one, yes, it is pure. I only have 1 component, and the last one you can see is not pure. And you should be able to ID what your impurities are. So this is something else from like also with experiment 5. Maybe you should take note of. Again, just explain why one might have more than one spot. So here, this is talking about how you can have more than one spot in a band because this was done by extraction. So this was your first extraction fraction, this was your second one, this was your third one. So I would assume this one was like your 3-nitrobenzoic acid fraction, or the Na, the sodium bicarb, and this is sodium hydroxide, or the like 2-naphthol one, and this one is your 1,4-dimethoxybenzene, or the organic layer. And so you can see I have residue. I wanted only this spot, and I only wanted this spot. I only wanted this spot, and this spot, but you can see I have residue of other material, and you should be able to identify those. So my extraction wasn't that great. Once again, I was separating based on what I saw, like layers, so as it drained, maybe some of the residue went down, or maybe I drained too early or drained too late. So you can analyze things like that. And this will be also very similar to like how the principle of experiment 5. Do the TLC make sense? Blah blah blah. So just be able to explain TLC as a method. So this is a method of assessing purity. That's the little tricky part of TLC. So it's assessing purity here. It's not the separation principle. This is the principle of separation. So that's what you want to pay attention to. And then here, another factor you have to look at. This is one of my favorite parts. So you can see, how does a changing mobile phase composition affect the TLC of compounds? And so what's going on is when you look at your mobile phase composition, of course you have a more nonpolar phase and you have more polar, and so you can use the like chart, I think page 35 or 34, to assess those eluting powers and all that. So here I know my nonpolar is hexane and my polar is ethyl acetate. And then we're like, what is triethylamine? So I need to draw the structure. If I don't know what it is, it's just 3 ethyl groups with an N in the middle, and it looks like this ninja star or something. Basically this, even more than just polar, yes, it is polar. This is polar. So yes, that's cool. But even more than that, wonder if I can, okay. So even more than that, you have to look at, if it's an acid or base. So this brings it back to extraction experiment. So acid plus a base gives you a salt, ionic salt, and water. And so here, you also classify these, are these acids or bases? So what happens is if you can I do an acid-base reaction? Is it possible? It seems weird that you would do that on a TLC plate itself, but it can happen. So your question is, can an acid-base reaction happen, like on the TLC plate while you're doing this? And so this is base, but I can see there's no protons. So of course this is basic. And then are there any acids here? If these were all bases, that's fine, it doesn't matter. But here, yes, I have a carboxylic acid. I have this H group that could get deprotonated. Like, you would look at pKs and figure out. And so what happens is if you deprotonate something, it could change your elution order, or it could keep it the same, it doesn't matter. But anyhow, when you deprotonate something, you get ionic salt. Ionic salts or ionic compounds are polar. You will lower your RF. So your part B will be lowered, your A will might be lowered, and your C it's not going to change, it's going to stay the same. And then another thing is, because your mobile phase, yes, this is polar, this is a smaller secondary effect, because triethyl means polar, you would assume, kind of like how acetone was 100%, when you did 100% acetone, you eluted all the way up on your TLC. Same thing here. So yes, everything's gonna push up a little and your RF will be greater. So yes, C will have a higher RF, but because of the acid-base reaction, which supersedes everything, this RF is just gonna be lower regardless. It's gonna be lower. These might be lower. So you would expect you would expect elution order. You would expect the elution order of B, then A, then C. I don't think A will deprotonate. I don't believe so, but yeah, you can just double check with pKs, but that's the idea. So my RF from lowest to highest would be BA, C. And that's not blood alcohol concentration, but okay. All right, I think that kind of summarizes what I had. Okay, and then experiment 5 post-lab questions. Again, there's another question like label, you forgot to label which solid which was which spot. And then you can just figure out RFs. RF is proportional to your polarity. So lower polarity is lower RF, and you can just figure out from that. Something like that is very valid to ask. And then you can figure out how many compounds you isolated, and that's based on purities and how many you had were pure. Here, blah blah blah. Changing the mobile phase, what happened? The 1090 was just way too slow, so you might have noticed that it didn't separate at all, and then you think it's not good, but you can just like use like 3070 or answer this like theoretically, and then yes, you would expect it to improve. Once again, like how I was talking about gravity. And then knowing how to change your mobile phase, again, here, now we have an acid, not base, like the previous one. So you want to go like, oh, do I have competing acid-base reactions? Are any of my mobile phase components acidic or basic? Are any of my solutes or compounds, anoids to separate acidic or basic? Will they interact and react with each other? Will that change my order of elution? Like, you should ask yourself that. And again, remember that experiment 5, similar to like experiment 3, you did column chromatography as a basis for separation. So you were judging when to separate your compounds. You were judging when to separate. So like, I'm gonna move it to collect another one. Like, you were judging where your layers were, just like experiment 3 with extraction. So yes, there is a little bit of human error. And then from how you extracted, you were assessing how good of a separation did you get? So purity, I guess, with TLC. TLC was not the method of separation. Column chromatography was. So just remember that. So you don't want to be saying, oh, I separated all 4 components like in the TLC and the column chromatography, so my column was successful because I separated all 4, because that's just TLC. That's not by column chromatography. You're trying to look at your different fractions and see this, not the original Spanish sample. That wraps up everything I have, and good luck on your final exam. Just remember, why. Okay, so I think, let me double check. Okay, so then just just like review everything, and then I think that wraps up all the separation and purification processes except for GC, but I'm not going to talk about that. And hopefully this just review for the midterm material really helps you for studying for the cumulative final. I'm sorry the videos are a little long, and you can just skip over sections where I'm just talking, where I might not be talking, I'm thinking or like writing stuff. So yep, good luck on the final exam, and hopefully this just helps recap the part that was in person. Bye.